Hello everyone, and welcome to this short introduction on using the SPS Conversion Assistant in Simscape Electrical. The purpose of the SPS Conversion Assistant is to provide support in the conversion of a specialized power systems model to Simscape native technology through three main mechanisms. The first mechanism is to convert the network topology. That is, connect the components together using Simscape physical connections. The second mechanism is to convert the components where supported. That is, to convert the component assembly and parameterization. The third mechanism is to provide a report that lists the result of the conversion and give information that can help you further refine your model in Simscape. Note that the Conversion Assistant may not perform a full conversion and that you must manually check the converted model and make adjustments as necessary. I will discuss some best practices as I go through some examples so that you can get the most value out of the Conversion Assistant. The first example is a DC RC circuit. We have a DC voltage source, a resistor, and a capacitor. Note that I have parameterized with variables. So I have C for capacitance, R for resistance, and VDC for DC voltage. We are simulating, in this case, in discrete mode with a time step of 50 microseconds. To perform the conversion, we go to the MATLAB command window and type SPS Conversion Assistant and use the model name, which in this case is A_SPS_RC. Press enter, and then the Conversion Assistant will get to work. So what you will see is you will see the models close and open while the conversion is occurring. And what we will end up with, once the conversion is done, is we will have a Simscape version of the model and also an HTML report. So let's first of all look at the report. So every conversion, you get a report like this, where it goes through the blocks that have been converted. It lists unsupported, partially supported, and fully supported blocks. And you get a summary, which includes some advice and guidance where appropriate. In this case, because I had the Power GUI solver set to Tustin Backward Euler, I'm being informed that Backward Euler has been selected in the Simscape local solver choice. We'll take a look at that as we go through. What I'd also like to do is just run this simulation. So I'm running the specialized power systems model now. We are storing current I and voltage V in the simulation data inspector. We'll look at that in just a moment. I'll just close this down and we'll take a look at the converted model. Now you may need to move some things around a little bit, but here is our converted model in Simscape. We look at the solver configuration. It's selected Backward Euler with the sample time TS, which we defined. And we also have the components. Now, if I just go in, DC voltage source C, we have picked up the variable names for the parameterization. That is a best practice. I will discuss this more in a moment or two when I discuss some other conversions. But best practice is to use variable names in your parameterization. Resistor, R, and capacitance, C. Note also that we've introduced a series resistance here. You can modify that. You can make that 0 if you wish. We've picked up the measurements, I and V. I'm just going to run this as is. And now we're going to look at the simulation data inspector and compare the results of the simulations. So I will look at current and voltage of the specialized power systems model, and then overlay voltage and current of the Simscape model. We see we have a perfectly overlaid response. In my next example, we are looking at a three-phase system, and I have included a three-phase pi section line. In specialized power systems, this is parameterized using positive and zero sequence values for resistance, inductance, and capacitance. Note again that I have used variable names in my parameterization. So we're going to run the conversion on this model. So SPS Conversion Assistant, model name, The conversion is complete. I'm going to run this simulation, the specialized power systems model. Then I will minimize this. We'll take a look first at the import assistant report. And so we see we have partially supported conversions. And so the information we are getting on this in the three-phase pi section line is letting us know that line currents might start from different values. Now, this typically is not a concern, but you should look at those values just to be sure when you run the simulation that everything is looking nice and tidy from that perspective. We've got some guidance here, but in this case, I'm not going to make any adjustments to this. The guidance is noted, but I'm going to look at my simulation, run my simulation, and do the comparison. If there are some differences, then I would take a look at the guidance and implement some of the guidance that's been suggested. But the first step would be just to run our simulation. I'm just going to move the solver configuration so I can see more of this model. So we have done the conversion, and I'm going to run the simulation. We'll take a look at the results first, and then I'll talk a little bit about some of the aspects of the conversion that have happened. So I'll just say phase B current. This is the specialized power systems result. Phase B for the Simscape conversion. And we'll just zoom in. And we can see that we have got a very good match. Very minor differences. This is a perfectly acceptable conversion. Now, in terms of the components that have been converted, remember that we had parameterized the pi section line with positive and zero sequence values in specialized power systems. The transmission line in Simscape accepts series and neutral, inductance and resistance, and you can see it has line-to-line capacitance and line-to-ground capacitance. So its parameterization is different. So what you will see is you will see these object classes that are being called in order to calculate the Simscape values from the specialized power systems parameterization. If I just copy one of these, I'm going to go to the MATLAB command window just to show you this in a little bit more detail. So we have a class associated with that component. You can see we've parameterized with our variables. And what we're doing here is we're selecting the series resistance value, so .r. And when we press return, we get the series resistance from the positive and zero sequence values. This is one of the reasons why we recommend that you use variables, because you want to have the variables show up when calling the class for those converted parameter values. If you just use numbers, the numbers will show up hard-coded in here, which means that you cannot readily reuse that component with different parameter values. So use variables to promote reuse of your converted component. In my next example, I am showing a conversion of a system which includes a synchronous machine. We also have a three-phase transformer and pi section line, which we used in the previous example. In this case, I have parameterized using a data structure. So my data structure is SM, and you see I'm accessing the parameter values through dot notation. Using data structures can be a more convenient way of parameterizing your component. We'll just run the conversion. The conversion is complete, so I'm going to run this simulation. We'll then take a look at the report, and then we will look at the Simscape model. So with our report, we've got information about the pi section line and the three-phase transformer being partially supported. So again, you're getting some information here. You don't need to take immediate action on the guidance. Best practice is to run the simulation, observe, and then make adjustments as necessary. You can see the additional components are fully supported. So I'm going to minimize my specialized power systems model. Let's take a look at the converted model. Let me just move the solver configuration again. And I want to spend my time with this example looking at the synchronous machine. In Simscape, you will notice that the Synchronous machine is an assembly of different components, and that assembly has been done automatically as part of the conversion assistant. If we look at the parameterization, note it has picked up the SM data structure, and there are some computations, such as field circuit current, where we have invoked the class to get the value, so the computed value from the parameterization that came from specialized power systems. And so the value of using a data structure is evident here, as these parameter values are being used in different components. It helps us organize the parameters effectively so that we can reuse this component in other models. So another point I would like to make with the solver configuration, the conversion has selected backward Euler. We could also try partitioning, and partitioning robust would be a good option to try because you may be able to get simulation improvement. I'm going to deselect the fixed cost iterations here for the use of partitioning robust. Let's just try this. I'll just save this model. We'll run this simulation and then do the comparison with the specialized power systems results. So let's look at phase A current. This is the phase A current from the Simscape model. Notice the initial transients here. Phase A current for our specialized power systems model. Let me just change the color to blue. And what we can see here is we have essentially overlaid results between specialized power systems and Simscape. If you do get differences in initialization, you can take a look at the guidance. You can make some changes in the initial values to bring your responses closer. But in this particular case, there is no need for us to take any additional action on this model. Our next example introduces power electronics. In this case, we are introducing a full bridge converter, just with some simple switching going on. Let's run the conversion for this model. The conversion is complete. First thing we'll do is run our specialized power systems model. And we'll take a look at the import assistant report. Again, we have got information regarding the solver choice and also some initialization guidance as well. Let's now go to our Simscape model, and we'll take a look particularly at the full bridge converter. So we're using the 4-quadrant chopper block here. You can see it's an assembly again. And parameterization, we are using the class. Now I have used a data structure here. So let's just go back to the specialized power systems model quickly here. I do want to talk about this. So you can see that I have defined a data structure FB, FB.RON for the on resistance, FB.ROFF for off resistance. In the conversion in Simscape, you notice that we've picked up the FB.RON, but it is hard-coded ROFF as that numerical value. You could change this. You could go in there and type FB.ROFF, but that is a change that you may or may not want to make. With the off resistance, not so important for subsequent use. RON may be what you're wanting to change, but you can make those modifications. And this is why the manual inspection is important, so you can assess the parameterization and make changes as you see fit. Let's run this simulation, and then we'll compare results. Let me just deselect that previous model, and we'll look at IDC for the H-bridge, IDC for the Simscape conversion. And again, these matches are very acceptable. You notice here, though, there is just a 1 time step delay here in this response, but nothing dramatic. with this comparison. It is very acceptable. In my final example, I just want to make the point that you can do a conversion on a single component. In this case, I have a three-phase fault. You will notice it is just a component. It is not connected to a fuller system. So you have this flexibility as well. If there are individual components you just want to check using the conversion assistant, you can do so. So let's just run the conversion assistant for this single component. So the conversion is done. This model won't execute because it's just a component. So we'll just take a look at the conversion report. So again, there is some guidance here on what you may need to look out for with the conversion. And now if you look at the converted component, you can see the conversion here. And I've defined some parameters, T on, T off, RS, RG, etc., which are picked up by the object class to do the parameter calculations for the Simscape models. For more information on the use of the SPS Conversion Assistant, please refer to the online documentation. So there is a page on the function itself, and if you scroll to the bottom, you also see there is another page, Upgrade Specialized Power Systems Models to use Simscape Electrical blocks. Also, please refer to this. There is some more information on considerations for performing conversions. In summary, SPS Conversion Assistant provides support in the conversion of a specialized power systems model to Simscape native technology. We recommend that you use variables to define parameters so that converted blocks can be reused. Manually check the converted model and make adjustments as necessary. And please refer to online documentation for further information. Thank you.